Upon each novel finding, the cosmos continues to test us. Despite our modern technological progress, a substantial amount of gap still exists within the vast expanse. Undiscovered physical occurrences transpiring in the farthest reaches of our galaxy have the capacity to both terrify and astonish deep space investigators. Today, we shall discuss one such phenomenon, the universe's most potent magnets, boasting a shockingly elevated radiation level, magnetars. Over the past half-century, humans have encountered immensely powerful radiation originating from the depths of space multiple times. However, as is often the case with cosmic revelations, astrophysicists were slow to pinpoint the source. In 1979, 3 US Vela satellites tasked with monitoring Earth's nuclear tests detected an atypical gamma-ray burst. By 1992, astrophysicists hypothesized the existence of an unknown celestial body with an immense electromagnetic radiation coefficient. In 1998, a gamma-ray burst occurred in the Aquila constellation, with several measuring instruments, recording an inexplicable anomaly source tens of thousands of light-years away from us. In 2004, a brief moment of worldwide telescope disruption ensued, followed by a gamma-ray radiation wave impacting every cubic centimeter within our solar system. It was the most substantial burst in observation history. Presently, we are nearer than ever to comprehend the nature of this discovery. A magnetar is a neutron star with an extraordinarily potent magnetic field, roughly 10 to the power of 13 teslas. Trillions of times Earth's electromagnetic radiation. Magnetars are among the rarest and genuinely perilous phenomena humans have ever confronted. When a supermassive star nears its demise, a supernova transpires. Out of the numerous possible post-supernova outcomes, only one could result in the star's monetary transformation. Many are familiar with Russian roulette. Following the game's rules, a single cartridge is placed in the revolver's chamber. The odds of firing after spinning the chamber are relatively low, but when it occurs, the consequences are genuinely staggering. Nevertheless, scientists continue to debate the precise nature of this scenario. According to one theory, a star's internal energy and rotational power contribute to magnetar formation. If a neutron star forms during rapid rotation, the star's internal energy and its significant rotational power during the initial seconds generate an intense magnetic field. This process is known as a dynamo mechanism. However, an alternative theory posits that, following the accretion process, a magnetar could obtain energy from another star. Researchers discovered a mentor on an escape trajectory from our galaxy. Most known moving stars embarked on their paths due to supernovae in binary systems. This indicates that the accretion process occurs between two stars sharing a common mass center within a binary system. The material gradually transfers from one star to the other, providing the potential monetary with energy. A similar process occurs when a basketball spins on a hoop's edge. The spinning ultimately determines the ball's falling direction. The magnets rotate around their axes with exceptional speed, ranging from tens to thousands of times per second. Concurrently, their dimensions are remarkably small, typically spanning a mere 20 to 30 kilometers in diameter. For comparison, the Moon's diameter is 3,474 kilometers, approximately 173 times larger than the average magnetar. The mass, however, is a different story. A 15-kilometer diameter magnetar would weigh considerably more than our Sun, despite its size. Its extraordinarily dense interior is responsible for its high magnetic radiation. For instance, 1E 1048.1 to 5937, an anomalous X-ray pulsar, is located 9,000 light-years away in the Carina constellation. The star from which the magnetar evolved to possess a mass 30 to 40 times that of our Sun. The matter within these stars is so dense that a pen cap would weigh billions of tons. A human would be disintegrated within seconds of landing on the star's surface. Several years ago, NASA astronomers registered a phenomenon now known as a stack. Using the Fermi Gamma Ray Space Telescope, scientists received data about intense X-ray bursts. Their source was Magnetar SGR J1550-5418. This star's magnetic field is so potent that its crust occasionally ruptures, releasing vast amounts of energy through the fissure. These staircases are the source of pulsed electrical currents. Theoretically, if an active monitor of this kind was situated within the solar system's boundaries, the Earth's ozone layer and all organic life forms would be eradicated in mere fractions of a second. Fortunately, the nearest monitor is a safe distance away. Approaching a monitor is difficult not only due to its core's gravitational properties and energy flares during a stack. In a stable state, a magnetar's magnetic field can disrupt electrical devices hundreds of thousands of kilometers away, and within a radius of 1,000 kilometers, any object would be atomized. To categorize the difference in radiation, scientists divided monitors into two varieties using abbreviations, rather than full names, which are found in astronomical catalogs. SGR, a soft gamma repeater, and American Express, anomalous X-ray pulsar. Essentially, SGR and American Express represent different phases in the life of the same object. According to scientists, a monitor exists as an SGR pulsar for the first 10,000 years, during which it's visible in regular light and repeatedly emits bursts of soft gamma rays. Over time, it exhausts its properties and recedes into the invisible spectrum, observable to us only in the X-ray range as an American Express. Estimates suggest that, among billions of neutron stars, the number of known potential monitors varies from 30 to 150. Approximately 12 reside in the Milky Way, with the closest one, named 1E2259+586, being about 4 kiloparsecs or 13,000 light-years away from Earth. This monitor is a soft gamma repeater. If a stack were to occur on its surface, it would only slightly affect the ionosphere upper layers. Due to their small dimensions and relative distance from Earth, magnets cannot be observed using ordinary amateur telescopes. Infrared or X-ray sky scanning is typically employed for observation. However, thanks to their active magnetic field emission and radiation, these stars are easily detected using various instruments. In 2013, astronomers claimed to have discovered a monitor near a supermassive black hole in the Milky Way center. Detected by several orbital telescopes, including the Chandra X-ray Space Observatory, SGR 1745-2900 is just 0.3 light-years away from the black hole's edge. It remains the only neutron star discovered so close to an object of this magnitude. SGR 1745-2900 has been under observation since its discovery. A few years ago, its X-ray radiation level was declared significantly lower than that of similar stories. This revelation sparked numerous debates. Could the black hole nearby be responsible for these changes? After 2 years of observing SGR 1745-2900, astrophysicists concluded that, considering all factors, the distance of 0.3 light-years is insufficient for any magnetic or gravitational field interaction between the black hole and the monitor. The reason likely lies elsewhere. A magnetar's lifespan is relatively brief, approximately 1 million years. It's natural for its magnetic field to gradually wane throughout its existence. As we continue to study magnetism, researchers have uncovered new information about their behavior and life cycles. For instance, magnets have a relatively rapid cooling process compared to other neutron stars. This cooling occurs due to the intense magnetic fields that permeate the star's core, causing neutrino emission and heat dissipation. Over time, as the monitor cools, its emissions and activity decrease. Furthermore, manatees have been observed to emit powerful radio waves. In 2016, astronomers discovered a mentor emitting a colossal radio signal, which they named a fast radio burst, FRB. FRBs are intense, short-lived radio pulses from distant astronomical sources. The discovery of this radio-emitting mentor has provided valuable insights into the origins of FRBs, which have been a subject of great interest and speculation among astronomers. Magnets may also play a role in the formation of heavy elements in the universe. When a monetary form, its intense magnetic fields can cause the surrounding material to become highly energized, resulting in the synthesis of elements heavier than iron through a process known as our process nucleosynthesis. This process is crucial for the production of elements such as gold and platinum, which are found on Earth and throughout the cosmos. The study of magnets has important implications for our understanding of fundamental physics and the behavior of matter under extreme conditions. These celestial objects push the boundaries of our knowledge, challenging our understanding of magnetism, gravity, and the nuclear forces that govern the universe. Additionally, the study of magnets can help us better understand the processes that occur during supernovae, providing valuable insights into the life cycles of massive stars and the evolution of galaxies. In the future, new technologies and observational techniques may allow us to further unravel the mysteries of magnetism. Advanced space telescopes, such as the upcoming James Webb Space Telescope and the proposed Lynx X-ray Observatory, may provide even more detailed observations of these extreme objects. Additionally, collaborations between astronomers, physicists, and computational scientists could lead to improved models and simulations of magneto behavior, helping us to better understand these enigmatic celestial bodies. In conclusion, magnets represent some of the most extreme and fascinating phenomena in the universe. As we continue to study them, we gain valuable insights into the fundamental forces that govern the cosmos and the behavior of matter under unimaginable conditions. While our knowledge of magnets has significantly expanded over the past few decades, there are still many unanswered questions and exciting discoveries awaiting us as we peer deeper into the depths of space.